Hello everyone, I hope you're enjoying the conference. I've seen a lot of great talks and amazing speakers, really enjoying it. Unfortunately, I couldn't travel to Berlin, but the organization was amazing and found a way for me to deliver my talk. Really appreciate it. Thank you all for joining my session, and let's talk a little bit about network service mesh. Before we get into the talk, let me introduce myself. My name is Ricardo Castro, and I'm the lead SRE at ANOVA. ANOVA is the global leader in remote monitoring of industrial assets. We provide industrial Internet of Things solutions that enable improvements for our customers in efficiency, safety, service, and profitability. We have more than 2,000 customers worldwide, we operate in more than 80 countries, and we monitor more than 1 million assets. And these numbers keep getting bigger and bigger. So, what will we be covering today? We will start by taking a look at traditional service meshes. We're going to do a quick recap where we will refresh what problems it addresses and what are its main components. Afterwards, we'll take a look at where they fall short. We will see some of the use cases where they don't work or where the solutions they propose could be better. We will then move on to talk about network service mesh. We will cover on a very high level what it is and what are some of its key concepts. We will then briefly take a look at some of the interesting NSM concepts you should take a look after this talk. And before we go, I'll point you to some interesting resources where you can learn more. So, let's start with complexity. Microservice architectures build applications as a collection of loosely coupled services. In this type of architecture, the goal is for services to be fine-grained and the protocols lightweight. The main objective is for teams to bring their services to life independent of other services. By building loosely coupled services, there's a reduction of the types of dependencies and the complexities around it. But that's easier said than done, right? Reliably managing network connectivity in distributed systems introduces its own set of challenges. Things like service discovery, load balancing, fault tolerance, distributed caching, metrics collection, and security are just some examples of the concerns that bring with distributed systems. So, how can a service mesh help us? A service mesh is a connective tissue between all of our services. It adds additional capabilities like traffic control, service discovery, load balancing, resilience, observability, security, and so on. A service mesh allows applications to offload these capabilities from application-level libraries, and it allows developers to focus only on differentiating business logic. Typically, a service mesh has two main components, the data plane and the control plane. The service mesh data plane consists of business services alongside their sidecar proxies responsible for all the traffic. The control plane comprises a set of services providing administrative functions necessary to the control of the service mesh. There are many service mesh implementations, and they can help us in many ways. Here we can see just a few of them, and you might be using one of them already. You might be delivering awesome functionality by leveraging one of these solutions. So, where do they fall short? Service meshes work well within a runtime domain, but often workloads need to collaborate with other services that are outside of the runtime domain to deliver full functionality. But what are runtime domains and connectivity domains? A runtime domain is essentially a compute domain that runs workloads. Traditionally, there's exactly one connectivity domain in a runtime domain because connectivity domains are tightly coupled with runtime domains. What does this mean in practice? It means that only workloads that are inside a runtime domain can be part of a connectivity domain, and each workload has only one option for a connectivity domain. Like we've seen earlier, microservices is a popular cloud-native architecture, and it's all about loose coupling. To really take advantage of this approach, microservice components need to at least depend on each other. Application service meshes work well within a connectivity domain and they target layer 7 payloads like HTTPS. They can help cloud-native workloads achieve loose coupling through functionalities like service discovery or fault tolerance. But fully fledged services are seldom confined within a single runtime domain, and therefore a single connectivity domain. Services have to spawn across multiple connectivity domains to collaborate with each other. Let's now explore some of the use cases where traditional service meshes fall short and when will network service mesh can do to mitigate those challenges. An example scenario is the multi-cloud hybrid cloud setup. In this scenario, you have several different and independent clusters which can be on a public cloud, private cloud, or on premises. Workloads in each of these clusters need the ability to talk to each other. You can think of this scenario as an inter-cluster networking, but from the point of view of the workload. In short, we have workloads running on different runtimes and connectivity domains, and they need to talk to each other. Another example scenario is the Multi-Corp extranet scenario. Here, also, workloads from different clusters need to collaborate with each other independent of their connectivity domains. The major difference between this and the multi-cloud hybrid cloud setup is that you now have different domain of administrative controls. This means that you have different organizations managing their own runtime and connectivity domains. Yet, workloads inside each of these domains need to work with each other. Service mesh balkanization is yet another example where traditional layer 7 service meshes fall short. Traditional service meshes work well within the same Kubernetes cluster, for example. And when local meshes need to collaborate, you usually link them through gateways. They're typically programmed with layer 7 static routes, which are both hard to scale and maintain. Traditional service meshes can't guarantee reliable networking here because they assume there's a reliable layer 3 under them. This is usually true inside one cluster, but can't be guaranteed beyond that. And last but not least, we are going to look at the multi-service mesh scenario. Typically, clusters can only support one service mesh. But in many circumstances, workloads will need to interact with services that are running on other service meshes. Think, for example, about a workload on Organizations 1 cluster using Istio needing to communicate with a workload that's running on the workload on Organizations 2 cluster that's leveraging Linkerd. In all the four scenarios that we've just seen, there are solutions, but they're not optimal. It would be a lot easier if they could treat workload communication in a transparent way, independent of where they're running. And this leads us to Network Service Mesh, or NSM for short. I'm lazy and Network Service Mesh is a bit long to keep repeating, so I'll use NSM as much as possible. So, what is NSM? NSM is the hybrid multi-cloud IP service mesh that enables L3 zero trust per network service connectivity, security and observability, works with your existing CNI, provides per workload granularity, requires no change to Kubernetes and no changes to your workloads. NSM tackles the scenarios that you've seen previously in this talk by allowing individual workloads to connect securely independent of where they're running. Your runtime domain provides inter-cluster connectivity and NSM doesn't require any changes or interferes in any way. And while it supports popular platforms like Kubernetes, it's not limited to it. Before we take a look at its key concepts, what are some of the examples where NSM can be useful? A common flat L3 domain that allows DBs running in multiple clusters, clouds, hybrid, whatever, to communicate with each other, for example, to perform DB replication. A single L7 service mesh like Istio, Linkerd, Consul, Kuma, or any other, connecting workloads running on multiple clusters, clouds, or on-prem. A single workload connecting to multiple L7 service meshes. And workloads from multiple companies connecting to a single collaborative service mesh from across company interactions. So basically the examples that we've seen previously where L7 service meshes fall short. Let's now dive into network service mesh's key concepts. And what we will be covering are network services, network service clients, endpoints, and vWires. We'll then take a look at Network Service Mesh API and at what are registries. So, Network Service Mesh is, in Network Service Mesh, a network service is a collection of features applied to network traffic. These features provide connectivity, security, and observability. A network service client is a workload that requires a connection to a network service, and it does so by specifying the network service name. Clients are independently authenticated through SPIFE-ID and must be authorized to connect to the requested network service. In addition to the network service name, a client can declare a set of key value pairs called labels. These labels can be used by the network service to select the proper endpoint, or they can be used by endpoints themselves to influence how it will provide the service to the client. An endpoint, also called network service endpoint, is the entry point to the network service to a client. The network service is identified by its name and it carries a payload, either IP or Ethernet, with IP being the default. Network services are registered within a network service register. So what can be an endpoint? An endpoint can be a pod running in the same Kubernetes cluster, a pod running in another Kubernetes cluster, a VM, any aspect of the physical network, essentially anything to which packets can be delivered for processing. What connects a client to an endpoint is known as a virtual wire or vWire. In short, a vWire acts like the virtual connectivity between a client and an endpoint. A client can request the same network service multiple times, and therefore multiple vWires connect a client to the requested endpoint. The vWire has a contract that establishes its rules, and those rules can be found in the NSM's documentation. Now let's take a quick look at the NSM API. It includes request, close, and monitor. A client can send a request gRPC call to NSM to create a vWire between a client and a network service. To cause a connection between a client and a network service, a client can send a closed gRPC call to the NSM. A client may also send a monitor gRPC call to the NSM to get updates on the status of the vWire between a client and a network service. Why would he do that? Because a vWire between a client and a network service always has a finite expiry time. So the client may, and usually does, send a new request message to refresh the vWire. If a vWire exceeds its expiry time without being refreshed, the NSM will clear up that vWire. So the monitor connection call allows clients to keep its vWire open. Let's turn our attention to registries. As with any other mesh, NSM has network service registries, in which network services and network service endpoints are registered. A network service endpoint provides one or more network services. It registers with a registry a list of network service by name that it provides and the destination labels that it is advertising for each network service. As seen previously, a network service is identified by its name and carries a payload type. Optionally, a network service may specify a list of matches. These matches allow matching with the source labels of a client that it sends its request to destination labels, advertised by the endpoint when it registers as the providing network service. For example, if a client provided no source labels with its request for the service mesh network service, it would not match the service envoy proxy for the first match, as we see here in this piece of code. And so would fall through to the final catch-all match with no source, with source selected, and it would be matched to the endpoint that advertised the network service named service mesh with the destination label service envoy proxy. Now, if a client provided a source label of service envoy proxy, it would match the first match and would be matched with the endpoint that advertised the network service named service mesh with the destination label service VEL3. Another interesting aspect of the NSM is that it also allows for multiple independent and mutually ignorant registry domains. The network service registry domain of a network service is indicated by the suffix by suffixing @domain to the network service name. In the example, we can see a network service name service mesh in the finance.example.com domain, and it would be service-mesh at finance.example.com. Now, this was a lot of information, so let's see how all of this works together. So on a high level, a network service mesh will register one or more network services with the NSM. It registers that list by name and the destination labels that it is advertising for each network service. A client can send a request to the network service to create a vWire between a client and the network service it needs. It can also close the connection. And because the connections have an expiry time, a client can monitor the connection to keep it vWire. The interesting part of the NSM is that it allows for workloads to request services independently of where they are running. It's up to the NSM to do the necessary wiring, creating the required vWires and allow communication between workloads in a secure way. Before we go, just a few more things. So this talk explores what issues network service mesh addresses and its key concepts, but there is a lot more that you can explore. You can take a look, for example, at interdomain, where a client may request a network service from any network service registry domain independent of where it's running. You should also take a look at some of its advanced features. The network service match process that selects a candidate endpoint for a certain network service mesh can be used to implement a variety of advanced features. Things like composition, selective composition, topologically aware endpoint selection, and topologically aware scale from 0. This can all be found in the documentation. Also important to note is the fact that since 2019, NSM has been part of the has been a CNCF project and is currently in the sandbox maturity level. If you don't know what the CNCF is, it's an open source foundation that promotes the adoption of cloud-native computing. The CNCF is a subsidiary of the Linux Foundation and aims to establish a vendor-agnostic community of developers and users and service providers to collaborate on open source projects. The CNCF projects are the foundation of cloud-native computing. The CNCF provides support, oversight, and direction for fast-growing and cloud-native projects, and includes such projects like Kubernetes, Envoy, or Prometheus. This means that the NSM is in very good company. I would like to leave you with some links so that you can explore NSM further. If you want to try it out, follow the Run Network Service Mesh in Kubernetes tutorial. It features a full installation as well as several example use cases. My suggestion is to go through the key concepts again and then solidifying them with some of the examples. If you want an introduction to the NSM, follow the Webinare Network Service Mesh and Introductions. It gives you a very nice overview of the NSM. And of course, check out the NSM roadmap to see what's in the horizon and check networkservicemesh.io for the full documentation. And that was all from my part. To recap, we started by going through an overview of traditional service meshes. We then looked at what were some of the use cases where the traditional service meshes fall short. We then took a 10,000-foot overview of the NSM and some of its key concepts. We explored several concepts like endpoints, network services, as well as the NSM's API, among other things. And last but not least, because we saw a lot of information in a very short amount of time, we looked at some of the resources that allows us to know more about the NSM. I hope this talk was informative for you. Feel free to ask questions or to reach out to me in my social networks. Thank you very much, have a great day and keep enjoying the conference.